to look at the data from Splunk. The way now we have configured a cluster that we want to be connected to. We call those providers. Now we want to create an index. We call these virtual indexes because they're virtual from the point of view of Splunk. And it's pretty simple. I'm going to choose a provider. In this case, the cluster that I copy the data to is called Hunk. I'll name this index called Hug, and I'll simply point to the directory where the data lives. There's a couple of options. You can customize your data partition underneath this with timestamp and stuff like that. But in this case, it's a fairly simple virtual index. That's another I have is the virtual index hub. I'll be able to immediately search that data. Right? Immediately go over it and look at that file start analyzing that file. Right? It's fairly simple. So now Splunk has recognized that this is an access confined source type, and it has extracted a bunch of fields. Right? So we have client IP, and just simply by clicking on this on the fields on the left hand side, you're able to see some of the top statistics. Like this is the top client IPs. Look at the top bytes. Look at the top. Once you do this, you can start going. Once the data is in Hunk, you could be using you can start using our search language to do more complex analysis. Like if you look at, I'm going to simply do a time chart over some time. We're going to look at count by status. This is the status field that shows up in the reports. And you can start now creating. You can start looking at time charts of all these requests that the users have that put in. Now we're seeing one of the 200s with a few, hopefully not maybe like. So now I showed you guys how so Splunk is Splunk's core competency is in logs, right? And this is something that we've done for over 10 years now. With Hunk, you're also able to do processing of any kind of data that you actually throw in to do. And the way we achieve this is through what we call data preprocessors. And this is something that is near and dear to me. We can do some image processing. With Splunk, you can do text data, you can look at logs, you can look at records. But to some people, that's boring, right? People can be throwing up data in Hadoop, and it could be images, it could be videos. So in this case, we've thrown some images, we've thrown some images into, and we're doing some simple color analysis on all that data. And to show you guys what is possible to be built on top of Splunk. In this case, I just selected a few colors that I wanted to look at this virtual index that I created there with images. Selected a few colors, and then I'm looking at the top images that match the color that I've selected. Right? And this is all done this was done by one of our developers in Splunk in a matter of a few days. Being able to pull up this entire interface, write the image processor, collect the data, and put everything up in this interface. And with that, I'll be more than happy to take any questions.
Any questions?
Well, in that.
So in the beginning when you were describing you said collect, prepare, and ask. 3 things. And you said ideally you should be preparing less and asking more.
Correct.
And my question is, what is the definition of value? You said you want to get value.
Right.
Is value visualization in your view, or is it something else?
Value in my mind is the ability to get answers, to get answers out of some questions that you have over your data. And whether those answers are a chart or a report or a few reports that you create, or simply counts, so the number of click-through rates or whatever you're interested in. So in my opinion, being able to get value out of data is being able to ask any questions out of your data that you have thought of either during collecting, preparing, or at any time afterwards. Just being able to get those answers is where it's down the line.
Any other questions?
Are there any constraints on questions which can be asked?
Are there any constraints on the questions that can be asked? That depends on, so the only constraint is whether you're going to be able to answer your question using the Splunk processing language. And we have somewhere in the 100 or so processors or commands that you can pipe your data through. So that's the only limitation that I can think off the top of my head right now. But you're able to see that you're asking questions of log data, and you're asking questions of images and sizable images.
So do you have any special adapters or major sources that you might call
Do you have special adapters
or like major sources of the log data?
Okay, so the question is, do we have any adapters for the major sources or source types of data? We end up holding similar sources, like in this case, Apache. We end up holding those source types. So yes, we do have a library. There's a library that we ship with. These are the common data formats that are out there. But we also rely heavily on people to write apps. It's usually our customers that are masters of their data, or they know their data very well. And we have about 300 or 400 apps on our own Splunk base. And some of these source types, this is where the source types are being defined. So for example, it could be the first 10 bytes or 15 bytes are of this load message or an IP address or a timestamp or the such and such field. We don't ship with, we don't claim to be masters of these adapters, but there's a tremendous number of them out there. Does that answer your question?
You handle dimensional data, and can you join across different data sources?
Okay, so there's a question up front. So the question is, do you handle drones, or do you handle different kinds of data sources? Yes, we do that. We're not very big on, we don't really believe in drones as they're implemented today outside in the database world of things. Primarily because with this explosion of data, it's almost intractable to join two huge data sets. So because we're able to do that as well. We do it slightly differently than what people do today. There's a question there?
Yeah, actually, I have a question both for you and for the previous speaker, the first speaker, about how do you deal with scalability issue, both for big data analytics as well as cluster management. Scalability.
Oh, how do we use scalability? Right. That's a great question. Scalability from our point of view is, or from Hunk's point of view, is the underlying. So we're building on top of Hadoop, right? We think of us as an application on top of Hadoop. So the scalability from our point of view is we depend on the platform to scale. But the application itself, we're MapReduce, so whatever MapReduce scales, that's how it will scale.
Is that manual, semi-automatic, or full-free automatic?
Our scalability is that manual. So the question is that manual, semi-manual, or automatic? Obviously, we cannot scale automatic, right? You will be able to see whether you need to increase the cluster because of the performance of a certain thing they want to start. This is something that we do see many of our customers do with Splunk Enterprise as they start adding more search capacity, more search load on their environment. Their performance of each and every search starts to drop, and that's when they get a notice on hey, there's time to add more searches.
So when you do auto scaling, how much is the latency? Auto scaling.
How much is latency?
Yeah.
So the latency that we're shooting here for is something under 3 or 4 seconds.
No. Not the big data analytics latency, auto scaling latency. When you scale your cluster, what is the latency?
What is the latency of us scaling the clusters?
When you scale your cluster instead of big data analytics, there are different kinds of latency. I'm talking about your cluster auto scaling latency. How much when you scale in and scale out, how much is the latency?
cluster in what sense? The latency of what? The latency of how
When
long?
you scale, grow your cluster or shrink your cluster, how long will it take you?
How long does it take for us to scale the cluster or for it to
For
be
you,
known?
for you to.
Well, we're not in the business of running clusters ourselves, right? We're in the business of
I
running a
understand
software.
you provide a platform. So, but if you don't provide,
Let's take this offline.
Anyway, if you don't provide auto scaling capability, then my question is nonsense.
Okay. Well, then we're not providing a cluster. Think of us as being an application on top of, let's say, Linux or on top of any other operating system. We'll take it offline. Okay.
In addition to the visualization, what key differences do you see between this and the Hadoop plus Solar architecture which is also coming up?
Okay, so the key difference is this ability to, as Splunk mentioned, this is a core difference in Splunk in how to look at data. Right, so you'd be able to put a schema on top of any data that, and you can change that from search to search. So any search gets its own schema. Right? There's this flexibility. We believe in giving users the flexibility to process the data however they want at query time without predefining anything upfront. And having this fully integrated platform that goes from being able to run a query all the way to see it and to see your results and visualize them and share them and publish them. I think that's one of the key differentiators. It's having something that is called everything is bundled up. I think there's.
Could you actually just elaborate one more time on the importance of Hunk versus before? Because Splunk does support Hadoop before, so.
Okay, so what's the difference between Splunk, between Hunk now and what Hunk was doing, or what we supported before? So before we had, in the market, we had about 3 apps. One of them was called Hadoop Connect, which was for moving data from Splunk to Hadoop when you wanted to export some data you had collected in Hadoop, and vice versa, bring data from Hadoop to Splunk, as well as some minor visualization of data that you had in Hadoop. Let's say you ran a bunch of Hadoop jobs and they output something, you would have the ability to bring those results into Splunk. Another app was the ability to age data out of Splunk into Hadoop. That was Shuttle. And finally, the third app was it's called Hadoop Ops. This was intended for looking at the logs of Hadoop and helping the operations team figure out the health of their environment. With the key difference with Hunk is the ability to process data in place. So your data is not in Splunk anymore. Your data lives in Hadoop. You've put your data there somehow. We don't really care. You put it there, but we're giving you the ability to process it in place where it is, and do that interactively and keeping it in the spirit of how Splunk does that.
I have one last question. How is this priced out?
How is this priced out? Lynn, do you want to take that question? It's based on the number of nodes in your Hadoop cluster. The pricing is online as well.
But you're not installing anything on the data nodes themselves. That seems a little arbitrary on pricing.
We're not installing anything on the data nodes, correct? So the deployment is you have a Hunk server outside of your Hadoop cluster, and this is able to now process and submit Hadoop jobs into the cluster. But no, we don't need to install anything on your cluster. As far as setup, that was the entire setup that you saw there.
Great, thanks.
Thank you guys. Thank you again.
Okay, so now comes to our final talk. Please welcome Jim. Jim is the CEO at Calcon. He's been building the business analytics and intelligence solution. This is early days of Oracle 6, I guess. Yeah. And now we're going to talk to you about his solution calling for DB, which is about offering the interactive query at scale. So please welcome Jim.
Hi. Jim Conley. Can anyone hear me okay in the back?
right, just the general agenda, a little info, background on InfinityDB, some underlying technology. So we'll talk about the MySQL part of the story. And you know, we're a specific tool in the stack. We'll talk about when it's suitable to use us when it doesn't make sense. We'll do some quick networks to share. So we do run on local server, run on ClusterFS, run on Amazon, run on HDFS also. That's new as of October this year. We are open source, you can source code is available here. The two things for us this year in October, we actually switched from a proprietary license model to a open source model. So we do provide support for that, but it's GPL-V2, you're able to use it without limitations at performance or syntax or scale or anything like that. That's what we do for us. We have an existing set of customers. We have about 50 customers to replace. There's probably like 3 clusters of companies that we work with. So certainly the ad serving companies dealing with taking web traffic, telco. We've got some space there, and it's online gaming. Game Loft's one of our biggest implementations with 25 servers in place. So where do you have it download? On Amazon, it's available on any of the availability zones. And we do run there off of EDS. So, InfinityDB, so it's an SQL for new capability or technology. It does have some database capabilities. We do a lot for joins, we do a lot for traditional database flavors, behaviors, but we also have some key differences to talk through. This is a goal from a Warner user group on the right. It's the idea that it opens up the big data to the SQL developers, to the people not comfortable with the Hadoop infrastructure. And in addition, there's a large number of tools out there that connect to MySQL that would be nice to plug into the Hadoop infrastructure, the Hadoop world. It's a purpose-built C++ engine, we built it from scratch. We actually do parallelism at the thread level, so we'll basically take a given SQL query, break it down into thousands, 10,000 or more very small jobs that each run in a small fraction of a second, and we'll just send it out to the distributed thread pool, and that'll be processed and returned back. So we use the term primitive to talk about the compute job. And that's actually a distributed job, so it does follow the central principle, the idea of moving the computation to the data. So there's a little bit, we have two things we talk about. There's a use model, that's sort of the central processing component, and a performance model, that's a distributed processing model. And a good cluster that a name node and a data node. You could also run the use model processor, which is a separate server. But typically you run the performance model process on the data node and allow for data sharing as easier. Talk for a little bit about an abstraction here. So we talk about the use logic performance model, which is basically a distribution of work. There's actually a queue in front of the performance model that picks up the next job, next period of operation, and will operate on the next one off of that queue. So the threads themselves aren't really dedicated to a given job. Instead, they're just reacting to the next job that comes up. So the thread could be working on query 1, and then the next job it works on might be query 3. Jump back to the first one, depending on the queue. You can actually prioritize based on users within the queue. One of the characteristics of that is it's actually okay for the CPU to use the CPU over time. That's actually a normal and standard behavior of the system. Assuming you had all the cores assigned to work on it. Okay, so a little better? Okay, how about this? Okay, sorry about that. What we've done in terms is we've mapped all the SQL operations that you can stack down to our primitive engine. So the filters, the joins, inner joins, outer joins, front clause, rear clause, select clause, subqueries, all the traditional group by distinct operations are all mapped to the distributed layer. And you can extend the underlying infrastructure by adding additional C++ libraries to the system. Those run as a full-featured functions, so it's not kind of needed to the intern to go build that out. Instead, it's part of the architecture. Internally, we talk about the data. We rely on data partitioning to deliver performance. So we have a two-dimensional data partition model with columnar. So this is a pure columnar architecture. I'll talk to a little bit more detail what that means from an end user standpoint. And we also partition the data by range of rows, by content, ascending keys, things like that. It's not really there's a pure column family that's out there. We don't follow the column family definition, but it says it's pure columnar architecture. We'll store data from column 1 into a completely discrete structure, and column 20 and column 21. One of the things that means is that you can actually add columns on the fly, right, without having to rebuild any existing structure. So there's whether it's the 101st or the 1001st column you're adding, you don't have to change any existing bytes on disk to support that. So it's not really schema on read, but it's actually much more flexible than traditional database systems. We have store metadata associated with each range of rows, and that's actually captured in a metadata layer that's stored in memory. We actually store about 64 bytes for every 64 megabytes on disk. And so there's about a 1:1 ratio there, so you can easily fit that in memory. And we do aggressive partition elimination. That's part of the underlying performance characteristics. So certainly any column type, including SQL, are obviously eliminated from I/O. We can do range-based partitioning based on filters provided. You can actually provide a filter on the dimension table, and that will be allowed to deliver I/O elimination on a fact table. And if you've got multiple filters in place, we'll actually intersect those for AND filters, for AND operations, and provide just the net results back out. Just a quick graphic, there's a term here called just-in-time materialization. So you've got columns involved in the query. Internally, we call things extents. That's just a partition of the data, horizontal partition of the data. So there's no full table scan involved unless you ask for every single. If you select star with no filter, there's no, it wouldn't show up in other use cases. We'll apply filters one at a time. So we did a filter one. We were able to reduce the rows based on some extended metadata information. We push the output from that operation to the filter 2, and then apply filter 3, and then any rows involved in the final select, final projection of the data are done last. So it's a just-in-time materialization. We actually won't do I/O until we satisfy the logic requirements for the previous operation. So all of that is actually in scope for one primitive operation. So the primitive does all this for you when you hit the code, so it's part of the optimizations that we have in place. I'm not going to walk through all of this, but there's a couple of things. So certainly you want to avoid I/O, right? That's the key to performance. So the top things kind of what we do to avoid doing I/O. But then the other part of it is just when you do have to do I/O, do it as efficiently as possible. So certainly you get the benefits of column compression. You can't use if you have a data buffer cache that works just like traditional database systems to offset I/O for this, so you can run from memory, but customers who do run from memory, and that's perfectly fine. And in addition, we actually don't have any random I/O built into our engine. So we basically do all scan operations after we apply these partitioning operations to it. And then that operation is fully parallelized across the system. And keep in mind, again, it's not a table scan, it's a range-based column scan. So we talk about this as scalable, fast, simple. What it ends up doing is there's no predefined indexes in place, and there's no predefined partitioning declarations required. So what it ends up doing is you can actually query on any column, any combination of columns. It's very easy to use. An example, we've got a customer who has demographic data, and they provide access to that data to their end users. Their customers, they want to be able to filter on any of about 500 different columns to find
demographic data of interest to them. So this they use our system to deliver a very flexible model to gaining access to the underlying data. So we are a MySQL engine. So we're a MySQL storage engine. In working with the guys over at MySQL for acquisition 1 and acquisition 2, they refer to our engine as a storage engine on steroids. So underneath, we actually will, the declaration is the very familiar MySQL declaration. Underneath it covers MySQL involved in the use validation, the initial syntax checking, and we actually take over execution of the query from that point in time, and MySQL is only involved again in the final, returning the results back to the MySQL client. So it is a MySQL storage engine, and tools that connect MySQL also connect with the we didn't want to reinvent that whole layer, that whole driver world. So benefits. So the user administration is MySQL user administration. The tools that work with it, these are a subset of our partner list, MicroStrategy, Jaspersoft, and Tahoe. And just allows you to combine the MySQL ease of use with Hadoop scalability. And then, built in with our common performance. The syntax we support. We actually support the base MySQL syntax with version 4 of our product, which is out now. We've added limiting functions. So that's actually our first extension beyond the base MySQL into some more advanced analytic functions. So that's new for us. Obviously, the syntax associated with index creation and partition declarations is not required, not needed. That's our world of syntax here. Let's see. Let me kind of, before I jump into kind of when to use this, let me kind of reset a couple things. So, we're here today, we have an open source product. We're actually looking for people to jump in and take a look at it. We have an existing customer pool that have proven it out in outside of the Hadoop space, but Hadoop is new. Right, so we need to look for customers to help us validate that. We're looking for lots of feedback on that. In terms of what we fit and what we're good for, the SQL is characterized by feeding rows back out to the client connection. So you're not using it for generalized transforms. You're typically this is part of the reporting layer. This is part of the end user. This is part of an ad hoc use case. This is part of a data scientist building models. Right, doing reporting on it. And the experience with the system is that it's actually very fast. The minimum latency in our engine is about a tenth of a second, maybe a little faster on that, depending on the size of your cluster. So it's very fast. Depends exactly on how fast your query is. We've got some benchmarks here again. We can kind of walk through the performance characteristics. But certainly SQL has got its own place in the Hadoop infrastructure. And it's not the idea that SQL replaces Hadoop. That's not the story. That's not the case. It's just that there's a use of SQL. There's a use of relational side by side with the existing Hadoop capabilities. So just when to use it. So there's sort of the idea that what's the query size, query vision, what's the number of records being pulled into the analysis. Our typical use case is millions or billions of records coming from a data set that's billions or trillions of records. And certainly if you have a large number of very lightweight versions of those technologies, we recommend instead of ours. But for very large queries, we do very well. And there's certainly no average query. And one of the things I believe is that as we've seen the underlying data scale, there's just becoming solutions that are optimized for one part of the workload tend to just dominate over solutions that attempt to be a general purpose solution. This is kind of just a rule of thumb. So for common storage, if you just did a select star where ID equals 1, you look for a single record out of it. The columnar storage like ours would typically be about an order of magnitude worse in performance from an IO standpoint than a traditional row-based system. So let's assume you have a 10-column table on this. We would have to touch 10 discrete files to satisfy a single record
not well suited for that style of operation. However, when you're talking about operations at scale, you're actually doing analysis of millions of rows or billions